Hello everyone. We are the authors of this ICMR paper. Today we are going to introduce our paper, naming the Exploring Potential Knowledge Correlations of Disease Diagnosis with Partial Labels. Disease diagnosis on chest X-ray images is a challenging multi-label classification task. It is the most widely available imaging examinations for screening, diagnosis, and management of multiple stratum diseases in the multimedia application field. However, automatic radiograph interpretation of chest X-ray images is currently a technological challenging task due to the complex phases which are heavily dependent on the expertise of radiologists with years of professional experience. Also, much significant progress has been made to deal with chest disease classification using convolution neural networks. It is still a multi-label challenging task due to the combinatorial nature of the output space. To address such multi-label tasks like chest X-ray 14 multi-diseases diagnosis, many researchers take a naive way by treating the objects in isolation and convert the multi-label problem into a set of binary classification problems, then predict whether each disease of concern presents independently. However, they ignore to utilize complex topology structure which has a strong correlation relationship between the disease pairs. For example, pleural effusion is more likely to appear with phenomenosis in presented in this paper. It is essential to consider the label correlation in multi-disease classification tasks for better understanding on the interdependencies. So, in this work, we propose a novel GCM-based end-to-end network called Disease Diagnosis GCM, which uses a nullable adjacency metric to dynamically null the conditional probability between disease pairs. Compared to the constant label correlation metric, our correlation matrix can be dynamically updated with gradient propagation during the GCM training, and therefore can capture nature label correlation in multiple disease classification tasks. Besides, to generate more general interpretations as the graph input, we first extract the fixed image level feature on the whole CXR image, then divide it into individual feature maps for each diseases. Our dynamic adjacency metric nulls such individual class features and can establish the correlation representations of diseases, which is consistent with expert experiments. In addition, to handle the incomplete labels, we design an adaptive curriculum learning strategy which relabels the uncertain labels into weak positive negative ones to fine-tune the pre-trained model to learn the potential contexts. Comparing to state-of-the-art, our method is much more robust and achieves the best performance on chest X-ray and chest per datasets. So next, we will introduce our pipeline. Graph convolution network takes advantage of learning strong correlation between nodes in graph. As shown in this paper and this figure, differs to previous works. We extract image level representations for individual diseases as the graph input. These individual features are more robust than mixed feature or word embedding features. Specifically, we first utilize a deep GCM network to extract features of the multi-label CXR images. Then, a transfer layer is applied to portion the feature maps into several blocks. Each corresponds to a particular disease class. After obtaining the representation of each disease, We send it to nodes of the stacked recurrent GCN to learn a dynamic correlation metric, and then train the final interdependent disease classifiers. Next, GCN works by gathering messages between nodes based on the correlation matrix, which is predefined in most researches. Although GCN-based approaches make significant progress, there are still rooms for improvement. First, previous works generally take mixed feature of the whole image or the word embedding of each label as the graph input to learn the correlation for a multi-label image classification. Such mixed features lack the differentiable representation for each disease, while the word embedding has no interpretable information in vision space. To dig out more robust interdependency of diseases, more meaningful and interpretable independent features of each disease needs to be represented in image space. Almost all GCN-based works explores a predefined correlation metric to map constant conditional probability between the label pairs. This metric is limited by human definition or the database scale. Meanwhile, some incongruent relationships are also hard to decide even for human and empirical statistics. Thus, more natural correlation needs to be explored by a dynamic learning and updating strategy rather than keep a constant correlation metric. This is our algorithm of the curriculum learning. At last, we will introduce the experiments section. Our framework is evaluated on two widely used datasets. The first is chest X-ray 14. The second is chest first. Our framework utilizes DenseNet with drop weight as the mixed feature extractor. As shown in this table, we first investigate the performance of our baseline model, DD-GCN, without adaptive loss and curriculum learning on the official split on the chest X-ray dataset with completely known label. It shows the comparison on the AUC scores with the state-of-the-art in detail. As compared with the 7 advanced method, our models achieves the highest average AUC score, demonstrating its strong ability. Our model outperforms that of the other work, which simply construct the image graph with different image inputs for clustering and loss the correlation of the CX square. This is our ablation study. In Table 3, we provide the ablation study on checkerboard validation set with AUC scores of top 5 diseases. We iteratively remove each component of our proposed method. We can find that every component contributes a lot to our final performance. Table 5 and Table 6 also provide some useful ablation. The first compare different correlation metrics, which shows that the dynamic metric is more useful and effective than the ones metrics and data-driven metrics. The latter shows that our method achieves the best performance only using the simple two-layer GCM. That's all. We want to provide a conclusion is that in this paper, we present a GCM-based end-to-end network called DD-GCN for multi-level chest disease diagnosis, which normally use a nullable adjacency metric to dynamically learn the conditional probability between the disease pairs. Besides, we feed each node with individual feature maps instead of general word embedding. In addition, we develop a curriculum learning algorithm to extract the potential information from the natural chest X-ray dataset with incomplete label. Experiments demonstrate that the proposed framework performs favorable against the state-of-the-art method on both two datasets. We believe that the null representation of correlation can help to predict the trend of other diseases in the future. That's all. Thank you. If you have any questions, you can email us.